Chapter 3.4, Equations and Graphs of Polynomial Functions. By looking at a graph of a polynomial function, you should be able to identify the following. The degree of the polynomial, that should actually read the minimum degree of the polynomial. As we saw earlier in this chapter, the maximum number of x-intercepts would equal the degree of the polynomial, but we can have a lower number of x-intercepts than the degree for many polynomials. So if we determine the degree based on how many x-intercepts we have, that would actually be the minimum possible degree of the polynomial. We can also determine the sign of the leading coefficient, the zeros, or the x-intercepts root solutions of the function, the y-intercept, in what intervals the function is positive, so where is the graph above the x-axis, or in quadrant 1 and 2, and in what intervals the function is negative, so where is the graph below the x-axis in quadrants 3 and 4. And when looking at the x-intercepts, or the zeros, or the solutions, or the roots of a function, we can also tell how many times the root occurs by what the graph is doing at that point. Taking a look at some examples here, the first one, it crosses the x-axis but does not change direction, so it continues going in opposite directions, which means that our degree would have to be odd. It's also going up from left to right, so that means that it would have a positive degree. And looking at how many x-intercepts we have, 1, 2, 3, and it says that those zeros are of multiplicity 1, 0 of multiplicity 1. What that means is that at the x-intercept, the graph is just crossing straight through, doesn't do anything weird, it just crosses through that point. We can write a possible polynomial function that could represent this graph. We have one negative x-intercept and two positive x-intercepts. We could say, let's say our negative x-intercept is at -2. Then our factor for that would be x plus 2. And let's say that our positive x-intercepts are maybe at 1 and 5. Then our factors for those would be x minus 1 and x minus 5. And we have a positive a value. Let's just say that it was positive 1. Next graph here, it also goes up from left to right, and it continues in opposite direction. So again, we would have odd degree, and we would have a positive leading coefficient. And over here I made a mistake. This should say, this here should say positive leading coefficient, not positive degree. Okay, and then looking at what this graph does at the x-intercepts, we have one x-intercept that it goes straight through. So that's a multiplicity of 1 like we saw over here, which means that that factor has an exponent of 1. But then we have another x-intercept where it touches and then bounces back off. When you have that, it creates a multiplicity of 2, which means that the factor for that x-intercept has an exponent of 2. So a possible example to represent this polynomial, we have one x-intercept that's negative, and then we have one x-intercept that's positive, and that one bounces back, so has a multiplicity of 2. Our a value, our leading coefficient, again is positive, so I'm just going to say that it's positive 1. So maybe we have y equals, let's say that the negative x-intercept is maybe negative 2, so x plus 2 with a multiplicity of 1, so exponent of 1 on that factor. And then the second one, maybe it's positive 3, so I could have x minus 3. That's a multiplicity of 2, so after the bracket for that factor, I need to put a squared. And then the third example here, our graph still goes from left up to the right. It's going in opposite directions. So again, we have odd degree and a positive leading coefficient. Looking at our zeros, here we only have 1, and it does this weird thing where it kind of like flattens out as it goes through. When that happens, it creates a multiplicity of 3 on that x-intercept. So we have an exponent of 3 on the factor. And an example of this possible polynomial, again, we have degree 3, we have a positive leading coefficient, so I'm going to say that it's positive 1, and then it looks like our x-intercept is at 0, so factors of x plus or minus 0, which is just x, so y equals x, and then that is a multiplicity of 3, a 0 of multiplicity 3, so x to the power of 3. Analyzing graphs of polynomial functions. Analyze the following graph and determine the following. Looking at our graph, it goes in opposite directions, the end behavior, going in opposite directions, so we know that our degree has to be an odd number. And again, this should actually say the minimum possible degree. So we know that it's going to be odd. Our leading coefficient, if we look at what direction it's going down as it moves to the right, which is a negative a value. So sign of leading coefficient would have to be negative, because it's going down to the right. Or another way to say that is it's going from quadrant 2 to quadrant 4. The end behavior, what is happening with the end? So this end is going up and this end is going down. So looking at our x values, as x approaches negative infinity, what's happening with the graph? The graph is going up, so the y values would be approaching positive infinity. As x approaches negative infinity, y approaches positive infinity. Then looking at the other side, as x is approaching positive infinity, the graph is going down, so y is approaching negative infinity. X approaches infinity, y approaches negative infinity. The zeros, x-intercepts, roots, solutions, let's take a look at those. So we have one at -2, 0 and one at 3, 0. What's happening to them? What are the multiplicity? We have a multiplicity of 1 at x equals to 3 because the graph goes straight through, no funny business. But at x equals to -2, it bounces off and goes back in the other direction. So that means a multiplicity of 2. So our x-intercepts are -2 with multiplicity of 2 and +3. The y-intercept, if we look at our graph, it looks like this line is 2. So 2, 4, 6, 8, 10, 12. Y-intercept is at 12, or we can write it as x equals 0, y equals 12. Same with our x-intercepts. We could write them as -2, 0, and 3, 0. The intervals where the function is positive. The function is positive when it's above the x-axis. So this section here is positive, which would be left of the negative x-intercept, so left of -2. So that would be when x is less than -2. It's also positive here, which is between the two x-intercepts. So when x is bigger than -2, but less than +3. -2 is less than x, which is less than 3. It's not positive when x is equal to -2 or 3, because then it's 0. 0 is not positive or negative. So it's only positive when it is left of this x-intercept, and also when it is to the right of that x-intercept, but to the left of the positive x-intercept. Intervals where the function is negative, so same idea, but now looking at where is the function below the x-axis. There's only one part here. It's this arm, and that happens when x is greater than the positive x-intercept of 3. X is greater than 3. Okay, so we've got most of our information. We still need the degree, or the minimum degree. We know that it's odd, so it'd be like 1 or 3 or 5 or 7, etc. We can look at the number of x-intercepts, because previously we learned that the maximum number of x-intercepts that a polynomial can have is equal to the degree of the polynomial. So if we know the number of x-intercepts from the graph, then we can determine the minimum possible degree for that polynomial. So in this case, we have 2 x-intercepts, but this one that bounces off, that has a multiplicity of 2. So we really count that as 2 x-intercepts. And then we have this one, which has a multiplicity of 1. So if we were to write an equation for this, we would have f of x equals a times our factors. We have a factor x plus 2 because we have an x-intercept at x equals -2. That factor, it has a multiplicity of 2, so we need to put a squared on that factor, and then times the other factor, which is x minus 3, because our x-intercept is +3. So just looking at this function, even though I don't have all the values, I can tell that my degree of this function would be 3, because I have an x squared term here, x squared, and then if I multiply it by this x, I would get an x cubed term. So my minimum possible degree of this polynomial would have to be 3. And a function that could represent this polynomial, let's find the a value, because this is often part of the question, is to write a function to represent the graph. So we need some values to plug in. We know the y-intercept, so let's plug that in. We have y equals 12 and x equals to 0. So a 0 plus 2 squared, 0 minus 3. 12 equals a times 2 squared times -3. 2 squared is 4. 12 equals a 4 times negative 3 is negative 12, and then divide by negative 12 on both sides, we would get that a is equal to negative 1, which matches with what we said. We said the sign of the leading coefficient has to be a negative because the graph is going down as it goes to the right, and we got a equals negative 1. So if we were asked to write a function that could represent this graph, it would be f of x equals negative x plus 2 squared times x minus 3. We have our negative 1 for our a value. We have our x-intercept at negative 2 with a multiplicity of 2, and then we have our x-intercept at positive 3, multiplicity of 1. Analyzing equations to sketch graphs from polynomial equations. To sketch the graph of a polynomial using its equation, determine the following information: the degree, leading coefficient, the sign of the leading coefficient, the end behavior, the zeros or x-intercepts and their multiplicity, the y-intercept, and the intervals where the function is positive or negative. Without using technology, sketch the graph of each function, label all intercepts. First one is y equals x minus 2 squared times x plus 1. The degree of the polynomial, we have x to the 2 here times x would be x to the 3, so our degree would be 3. The leading coefficient would be a positive 1 here. So leading coefficient is a positive. The end behavior, if we have an odd degree polynomial with a positive leading coefficient, then it goes up to the right. So it goes generally like this. So then as x goes to negative infinity, y is going to negative infinity, and as x goes to positive infinity, y is going to positive infinity for our graph. End behavior, as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. The zeros x-intercepts, so we have a factor of x minus 2, which means we have an x-intercept at 2. We also have a factor of x plus 1, so we have an x-intercept at negative 1. Next, the multiplicity of the zeros. Our x plus 1 factor has an exponent of 1, so negative 1 x-intercept has a multiplicity of 1. The x minus 2 factor has an exponent of 2, so the x-intercept of 2 would have multiplicity of 2. And then the y-intercept, to find the y-intercept, we sub in 0 for x. We get 0 minus 2 squared times 0 plus 1, which is negative 2 squared, which is 4, times 1, which is 4. So our y-intercept is 4 or 0, 4. And then we can graph our function, starting with our x-intercepts at positive 2 and negative 1. Our y-intercept is at 4, and we know that it goes straight through the negative 1 x-intercept, but bounces off the positive 2 x-intercept, and it's going to go up as it goes to the right. So it's going to be down here, cross through negative 1, get the y-intercept, come down to x equals 2, bounce off of that x-intercept, and continue back upward. something like that. This point is 0, 4. This point is 2, 0. This point is negative 1, 0. And there's a sketch of our polynomial. Next one. Y equals negative x to the power of 3 minus 8x squared minus 16x. The highest degree of our monomials is 3, so the degree of our polynomial is 3. And also our leading coefficient is the coefficient on the monomial with the highest degree, so that would be the negative x cubed term. So our leading coefficient would be negative 1. It's an odd degree, which means the two ends are going opposite directions, and it has a leading coefficient that's negative, so it's going to go down as it goes from left to right, so it'll be something like this. So our end behavior, as x goes to negative infinity, y is going to go up to infinity, and as x goes to positive infinity, y is going to go down to negative infinity. As x goes to negative infinity, our graph is going up, so y is going to approach positive infinity, and as x approaches positive infinity, our graph is going down, so y is approaching negative infinity. Next, doing the zeros and x-intercepts, we need to write this trinomial in factored form. I have a common factor of negative x. If I factor that out, I get y equals negative x times x squared plus 8x plus 16. Then I look at the trinomial inside the brackets, x squared plus 8x plus 16. Can I factor that? I would need two numbers that multiply to 16 and add to 8, which would be, we'd have negative x times, it would be x plus 4, or x plus 4 squared. That tells us that our zeros or x-intercepts or solutions or roots would be when x equals to 0 for the x factor, and then when x equals to negative 4 for the x plus 4 factor. The multiplicity of the zeros, the x factor doesn't have any exponents. It would be an exponent of 1, which means a multiplicity of 1. The x plus 4 factor has an exponent of 2, which means the x-intercept would have a multiplicity of 2. So negative 4, multiplicity of 2. The y-intercept, let's sub in 0 for x. Y equals negative 0 to the power of 3 minus 8 times 0 squared minus 16 times 0. Well, all of those would be 0, so y equals to 0. Or we can write it as 0, 0. And then we can plot our points. We have the y-intercept at 0, 0, which is obviously also an x-intercept. And then we have another x-intercept at negative 4. We know that it's a degree 3 and it's negative, so it's going to be going this general direction, so down as we move to the right. And we also know that it's going to bounce off this x-intercept, but go directly through this x-intercept, so like that. So it would have to go bouncing off this x-intercept, something like this. This point here is 0, 0, which is both an x-intercept and a y-intercept, and this point here is negative 4, 0. Graphing using transformations. Recall the effects of parameters a, b, h, and k on any graph y equals f of x. Apply these parameters to the graph of a polynomial function. So here is the equation of a polynomial function with the parameters shown. We have y equals a bracket b bracket x minus h close bracket to the power of n plus k. So we know that h is the horizontal translation left or right. Using mapping notation, x, the point xy on the original function, would go to the point x plus h y on the transformed function. K is the vertical translation up or down. Using mapping notation, a point xy on the original function would become x y plus k on the transformed function. A is the vertical stretch about the x-axis by a factor of a, and if a is negative, the graph is reflected in the x-axis. Using mapping notation, a point xy on the original function would become x and then a times y on the transformed function. And b is the horizontal stretch about the y-axis by a factor of 1 over b, the reciprocal of b. And if b is negative, then the graph is reflected in the y-axis. Using mapping notation, the point xy on the original function would transform to the point 1 over b times x and then y. Transform the graph of y equals x to the power of 3 to sketch the graph of y equals negative 4 bracket 2 bracket x plus 2 close bracket to the power of 3 minus 5. Let's start by writing out our parameters. We have an a value of negative 4, which means a vertical stretch factor of 4 about the x-axis. And because it's negative, we have a reflection across the x-axis. Our b is 2, which means we have a horizontal stretch factor of 1/2 about the y-axis. And it's positive, so there's no reflection. Our h value would be negative 2, because our general form has x minus h, so since we have x plus 2, then h would have to be minus 2, which is a translation 2 units left. And our k value is negative 5, which is a translation 5 units down. Then using mapping notation, a point x, y, when we apply these transformations, would become the point 1/2 x minus 2 and negative 4y minus 5. So if we were to draw the original function, which would be the cubic function, y equals x cubed, because we have a cube here, so we know it's y equals x cubed is the original function. If we were to draw that, 0 cubed is 0, negative 1 cubed is negative 1, positive 1 cubed is 1, 2 cubed is 8, and negative 2 cubed is negative 8. So the cubic function y equals x cubed looks something like this. And we can use these points that we just calculated and use to draw our y equals x cubed to draw our transformed function. Starting with negative 2, 8. X is negative 2, y is 8. Let's see what happens when that's transformed. We have 1/2 times negative 2 minus 2, and then negative 4 times 8 minus 5. which gives us so we have 1/2 0.5 times -2 and then -2 gives us -3. And the y value, -4 times 8 minus 5 gives us -37. So at that point, I'm not going to be able to fit on my grid. That's okay. We'll do the next point, which was when x is -1, y is -1. The transformed point would be 1/2 times -1 minus 2 and -4 times -1 minus 5, which is 0.5 times -1 minus 2 gives us -2.5. And the y value, -4 times -1 will be +4, minus 5 should be -1. We can plot that point, -2.5 and -1. -2.5, -1 right there. Next one is 0, 0. Plug that in. 1/2 times 0 minus 2, and then -4 times 0 minus 5, which would just give us -2 and -5. We could plot that point. -2, -5 down here. Next point is +1, 1. 1/2 times 1 minus 2 and -4 times 1 minus 5, which gives us 0.5 minus 2 is -1.5. Let's just make sure. 0.5 times 1 minus 2, -1.5, and then -4 times 1 is -4, minus 5 is -9. -1.5 and -9 down there. And then our next point, it doesn't look like it's going to be able to be plotted, but we'll do it anyways. 2, 8, 1/2 times 2 minus 2, and then -4 times 8 minus 5, which gives us 1/2 times 2 is 1, minus 2 is -1, and the y value, -4 times 8 minus 5, -37. So we can't plot that point either. But we have 3 of our points, and the one that was where the graph does that weird flattening out thing, that was at 0, 0, which became -2, -5. So when we draw it, the point -2, -5, our middle point, we're just going to kind of flatten out a bit like we did with the point 0, 0 on the original function. So it should look something like this. And that would be y equals -4 bracket 2 bracket x plus 2 close bracket to the power of 3 minus 5. I just realized the point -2, 8 that we transformed should actually be -2, -8, which would then change our point on our transformed function. That should be -8, that should be -8, which then changes our y value from -37 to -4 times -8 is +32, subtract 5 is 27. Determine the equation of least degree in factored form for a cubic polynomial with zeros of -1 and 2 with a multiplicity of 2 and y-intercept of -12. So it says least degree, but it also says a cubic polynomial. So in reality, we know that the degree is exactly 3. If it didn't tell us it was a cubic polynomial, if it just said determine the equation of the least degree in factored form of a polynomial with zeros of -1 and 2, multiplicity of 2, and y-intercept of -12, then we wouldn't know for sure if the degree is 3. So then we would just say that the least degree would be 3. It could be higher than that. It could be a higher odd number, but for sure it would have to be 3 because we have 3 x-intercepts, even though one of them is a repeat, but we have 3 factors. So our equation that we can start with is y equals a bracket. Since we have an x-intercept of -1, then x plus 1 has to be a factor. And we have an x-intercept of 2, so x minus 2 has to be a factor, and that has multiplicity of 2, so that factor is squared. Next, we know the y-intercept is -12, so we can sub that in so that we can solve for a. -12 equals a, 0 plus 1 times 0 minus 2 squared. Simplify, we get -12 equals a, 0 plus 1 is 1 times -2 squared. -12 equals a times -2 squared is 4. And then divide both sides by 4. And we get a equals -3. So our cubic polynomial would then be y equals -3 x plus 1 x minus 2 squared. Last example, 3 consecutive integers have a product of -210. Write a polynomial function to model the situation and find the 3 integers. Consecutive integers means in a row. So if the lowest number is 3, then it'd have to be 3, 4, and 5. Those are consecutive integers. We don't know what the numbers are, so we're going to let x be the smallest integer, then x plus 1 and x plus 2 are the next 2 consecutive integers. The question tells us the product of the 3 integers is -210. So we can write -210 equals x times x plus 1 times x plus 2. I want everything to be on one side, so I'm going to need to multiply the right side and then move everything to one side. So I'm going to multiply my 2 binomials together. -210 equals x times x squared plus 2x plus x plus 2. Simplify what's in the brackets. -210 equals x times x squared plus 3x plus 2. Multiply x into the brackets. -210 equals x to the power of 3 plus 3x squared plus 2x. And then move everything to one side. I'm going to add 210. I get 0 equals x to the power of 3 plus 3x squared plus 2x plus 210. Now we want to find any one factor of this polynomial. So we have p of x equals x cubed plus 3x squared plus 2x plus 210. Next we can use the factor theorem to find a factor of p of x. So because our leading coefficient is 1, we know that our possible factors are all the factors of 210, which is a whole lot. We know that we can cheat the system, though, by finding an x-intercept with our graphing calculator. Clear that. We have x to the power of 3, move out of my exponent. Then I have plus 3x squared plus 2x, and then plus 210. Graph that. And I don't really care about seeing the whole graph. I just want one x-intercept. I can see this one, but I can't quite tell which direction would be left and right of that. So I'm going to try zoom and zoom fit and see if that helps. Okay, there we go. I want to find my x-intercept, second trace, number 2, left bound, hit enter, right bound, hit enter, and it tells me that my x-intercept is at -7. So as a note here, use graphing calculator to find an x-intercept, which was x equals -7. Then we can use the factor theorem and plug in -7 into p of x. -7 cubed plus 3 times -7 squared plus 2 times -7 plus 210. And we should get 0. So let's try it. Bracket -7 close bracket to the power of 3. Move out of my exponent. Plus 3 times bracket -7 close bracket squared plus 2 times bracket -7 close bracket plus 210 gives us 0. So p -7 equals 0. Then x plus 7 is a factor of p of x. Therefore, x equals -7. X plus 7 equals to 0 when x is -7. X plus 1 equals -7 plus 1, which is -6. And x plus 2 equals -7 plus 2, which is -5. So the 3 consecutive integers are -7, -6, and -5. And we can double check that those multiply to give us -210. -7 times -6 times -5 is -210. That brings us to the end of Chapter 3, Lesson 4.